Good afternoon, and welcome back to Day 2 of Thermal Live 2019. I'm Jennifer Arroyo with Electronics Cooling here in Philadelphia. As the producers of Thermal Live, we'd like to thank you once again for joining us. Our next presentation comes from Kimberly Bixie, Applications Engineer with Advanced Cooling Technologies. Kimberly will review strategies for managing the rising waste heats from MOSFETs, IGBTs, and other power electronics modules using two-phase technology, with a focus on loop Thermos and pumped two-phase solutions. The presentation will last around 35 minutes and be followed by a quick 10-minute Q&A session. We want to hear from you, so please locate the Q&A panel on your screen and submit as many questions as you'd like. We'll try to get to as many of those as we can during the Q&A session at the end. If you'd like a copy of this presentation, downloadable slides are available under the Resources tab at the bottom of your audience console. Now, without further delay, please welcome Kimberly.
Thank you, Jennifer, and welcome all to today's two-phase webinar. As discussed in the introduction, we will dive into the methods to mitigate the rising challenge in power electronic thermal management. Power electronics is a specific type of electrical engineering that deals with power conversion and control. Now, this ranges from system control, where you have switches and contactors, to power and energy conversion with motor drives, power supplies, and inductors. And then all the way to the electronic devices. This is where we have those circuit boards with MOSFETs and IGBTs, which drive extremely high power. The electronics industry is moving in a direction that requires advanced power electronic systems. These advanced systems are used to develop electric vehicles, those newer, better electronic devices, and even smart homes. In order to continue the improvements, it is imperative that these systems have properly designed thermal management. A device that has an inefficient thermal system will show reduced and inconsistent performance to even shorten lifetime. In this webinar, we'll dive into those advanced thermal management strategies. Those strategies will be critical in handling the higher power requirements that are developing within this industry. Typically, the industry turns to an off-the-shelf solution for thermal control. These solutions include the standard aluminum thinned heatsink that relies on conduction for thermal spreading and natural convection to dissipate the heat. That thinned heatsink, however, is limited by extreme conduction gradients and high heat fluxes in those newer, high-powered power electronics. The next tier for thermal management is an off-the-shelf fanned heatsink. A fanned heatsink still requires conduction for thermal spreading and will have conduction gradients determined by the selected material, but does utilize forced convection to ultimately remove the heat. The forced convection can occasionally overcome the challenges created by the thermal gradient. However, they are still limited by airflow and high heat fluxes. The last, but not least, off-the-shelf cooling strategy for power electronics is the liquid cold plate. The single-phase pumped liquid solution has the ability to reduce conduction gradients, as well as offering temperature control. However, it struggles with high heat fluxes and temperature uniformity. It is therefore important to identify and understand advanced thermal strategies that support the cooling of power electronics when those typical off-the-shelf solutions fail. As mentioned earlier, today's webinar will detail 3 types of cooling strategies that were developed and produced by Advanced Cooling Technologies: the enclosure cooler, loop thermosiphon, and pumped two-phase. All 3 of these technologies leverage two-phase heat transfer. Two-phase heat transfer utilizes the latent heat of a substance. But what is latent heat? Well, specific heat is the amount of heat per unit mass needed to raise a substance 1 degree Celsius. Or in other words, it's the amount of thermal energy a substance absorbs as it raises in temperature. Latent heat, however, is the amount of heat required to change the phase of a substance without raising the temperature. Or really, it's the amount of thermal energy required to break those intermolecular bonds of the substance for it to change phase. Now, water is a perfect example of this. Water is just this awesome thermal fluid due to those hydrogen bonds which occur between molecules. the hydrogen bonding in that liquid phase leads to a high latent heat value of 2,257 kilojoules per kilogram. Its specific heat is only 4.187 kilojoules per kilogram degrees Celsius. This means that water will absorb 540% more thermal energy per unit mass as its converting phase compared to it raising in temperature. However, in the power electronics industry, water is not always accepted. Therefore, we must identify other strong thermal fluids. Water, we identified, has a high latent heat of vaporization, but it's important to understand the other factors that lead to a strong thermal fluid. This is calculated by the figure of merit. The figure of merit identifies a fluid boiling heat transfer capacity and is equal to the liquid density times the surface tension times the latent heat, all divided by the liquid viscosity. Fluids with high latent heat, high surface tension, and low liquid viscosities are all ideal in two-phase heat transfer. For fluids such as methanol and ammonia, they have strong merit numbers, as shown in the chart, and are used regularly in the thermal industry for low temperature control. For the power electronics industry, refrigerants, like the ones shown on the figure to the right, with high figures of merit or high boiling heat transfer, are typically used to mitigate any leakage concerns. There are two ways to utilize the latent heat of vaporization, either passive or actively. A passive heat transfer device, known as either a heat pipe or a thermosiphon, operates in a completely closed system. Since the system is in a vacuum, it therefore will operate along the saturation curve of the working fluid selected. At the hot spot of the system, otherwise known as the evaporator, the working fluid will vaporize. This vaporization causes a slight pressure difference to occur within the pipe. That pressure difference will cause the vapor to move to the area of lower pressure, and once there, will condense. The condensed liquid will flow back to the evaporator, either from capillary action in a heat pipe or gravity in a thermosiphon. Typically, these passive two-phase devices have about a 2 to 5 degree delta across the length of the system. The ACT enclosure cooler can be considered both an active and passive cooling device due to the use of a fan. It leverages both the passive two-phase heat transfer and passive conduction heat transfer qualities. The next two slides detail ACT's two standard enclosure coolers and show the benefit of adding that two-phase heat transfer to a system. The simplest form of the enclosure cooler is called the HSC, or heat sink cooler. This cooler uses a sealed, forced air finned heat sink that conducts the heat from inside the enclosure to the outside. Hot air from inside the enclosure is brought to the cooler via the internal fan. That hot air heats up the fins and conducts to the fins on the external side of that cooler. This is typically at a rate of 167 watts per meter Kelvin, or via the thermal conduction of aluminum. The heat that is conducted to the external fins is then dissipated to the external ambient via a fan. These are used in rough environments that require NEMA rating and isolation from the external environment. The heat pipe enclosure cooler, or HPC, follows the same concept as the HSC. However, instead of relying on the conduction between the internal and external fins, heat pipes are applied. These passive two-phase heat transfer additions increase the effective thermal conductivity to roughly 10,000 watts per meter K. In both the HPC and the HSC, the internal enclosure temperature requirements must be higher than the external ambient. Each enclosure cooler is rated to remove a certain number of watts per delta T. For example, the enclosure cooler shown on this slide, the HPC 40, will remove 40 watts for every degree C delta there is between the internal and external temperatures, given that that external is lower than the internal. Because the HPC utilizes two-phase heat transfer, more power is removed per degree C. The largest HPC unit has the ability to remove 80 watts per degree C delta. Now, these are typically used in enclosures that require that NEMA-sealed rating and tend to hold variable frequency drives that generate a lot of waste heat. Two-phase heat transfer is used in many other power electronic systems as well that don't always require that completely sealed solution. These applications can leverage a loop thermosiphon, which has the capacity to remove up to 75 kilowatts of waste heat. When we initially discussed the passive two-phase heat transfer device, we looked at a linear heat pipe and thermosiphon design. In the linear system, the vapor and liquid flows in different directions in the same pipe, as shown in the figure on the far right. A loop thermosiphon, however, is still the same passive two-phase cooling solution, but the liquid and vapor both flow in the same direction along a continuous loop. The liquid pools at the base of the loop by the evaporator zone. At the evaporator, the liquid vaporizes. Again, that vaporization creates a pressure difference in the closed system. The pressure difference causes the vapor to flow to the cooler area. At the cooler, low-pressure area, the vapor condenses and removes the heat. The liquid then returns to the evaporator via gravity. This system is therefore able to handle higher amounts of power than the typical thermosiphon. Now, one of the great things about the loop thermosiphon is that there are really only 4 basic components. It has the evaporator body, which can be as large as needed, so long as it is gravitationally lower than the condenser. And then it has the condenser body. Now, the condenser body is sized to meet whatever required thermal performance is spec'd in your system. Then you have the working fluid selection and the vapor and liquid lines. Again, since this operates in a loop and utilizes both gravity and the latent heat of vaporization, we are able to handle higher heat transport capacity, go longer distances, and have a higher two-phase heat transfer efficiency. And since it is completely passive, it has 0 operating costs. The next 2 slides detail a case study in which a loop thermosiphon was used to manage the waste heat of a power electronic device. The case study requirements included the ability to handle up to 11 kilowatts of waste heat, have a thermal resistance no greater than 0.005 degrees Celsius per watt, have an operating environmental temperature range that went from negative 55 degrees Celsius to plus 50 degrees Celsius, and a storage temperature range of the same. The system also required 0 moving parts, a working fluid that was dielectric, and a lifespan that would be greater than 10 years. The case study focused on an IGBT device that was capable of generating greater than 10 kilowatts of waste heat with a high heat flux. The study was set to hold the system below 70 degrees Celsius at that 10 kilowatt range. The 2 graphs at the bottom of this page detail the cold plate temperature increase as the power increased. When the power reaches 10 kilowatts, the cold plate maxed at 67.5 degrees Celsius. The graph on the right displays the temperature of 9 thermocouples situated across the plate. This case study resulted in less than 10 degrees C delta across the cold plate, even with that high heat flux generating device. Now that we've discussed the passive two-phased cooling solutions, the enclosure cooler and the loop thermosiphon, let's dive into the active two-phase cooling solution, or pumped two-phase. Pumped two-phase is used when designers have about 10 kilowatts to maybe even 300 kilowatts of waste heat and require that high-performing cooling system. Now, an active two-phase solution operates on the same concept as the passive solution. You're still using that latent heat of vaporization to remove the thermal energy from the component. However, unlike the passive solution, it is not in a completely closed system. Here, it is more similar to a single-phase solution. And just like the typical single-phase solution, a pumped two-phase system includes the heat exchanger, reservoir, pump, and cold plate. There's one main difference. In a pumped two-phase system, the liquid enters at saturation level. It will therefore vaporize at the controlled desired temperature. Here, we have a pumped two-phase system that was designed with 4 cold plates, 2 in series that are then in parallel. This system also includes a filter to ensure the refrigerant is clean before it enters the pump, and an accumulator. An accumulator is used to store excess refrigerant to compensate for the volume change from the multiple cold plates. You can see at the condenser is where heat exits the system, and at the cold plates where heat enters the system. In a typical single-phase solution, high heat flux is a challenge. The only way to mitigate this challenge is to increase the flow rate. The increased flow rate leverages specific heat to remove the thermal energy from the heat-generating component. But in that two-phase system, those heat fluxes are less of a concern because of the use of latent heat of vaporization. It's our common theme in today's webinar. But wait, it gets even better. The lack of need to increase flow rate means that a pumped two-phase system can have smaller pumps than the typical single-phase system. Smaller pumps means less power consumption and less parasitic losses in the energy industry. The reduced flow rates also result in reduced erosion on the plumbing of the system. But the main benefit is the ability to reach a high degree of isothermality. Now, by utilizing specific heat in single phase, you are raising the temperature of your fluid as you absorb the thermal energy from the component. This means that every component down the line will see a different fluid temperature than the one before it. But with two-phase, by setting the saturation temperature and utilizing the latent heat of vaporization, your fluid remains a constant temperature, which means that every component will vaporize at that same temperature and will see the same temperature down the line. Now let's take a look at some numbers to fully understand the comparison between single-phase and pumped two-phase cooling. For this example solution, we have a system that has 80 kilowatts of total power. For a single-phase PAO loop, we would need a flow rate of 134 liters per minute to manage that thermal load. This means a pumping power of 5.3 kilowatts. However, if we were to replace that system with a pumped two-phase using R245 refrigerant, we could manage the thermal load with a flow rate of only 25 liters per minute. That would be an 80% reduction in flow rate versus a single-phase solution. Now, that reduced flow rate would only require a 250-watt pump, which is a 95% reduction in pumping power versus a single-phase solution. But there certainly are things to consider when applying these systems. Since the fluid must enter at saturation, managing flow instabilities and pressure drops is a concern. The design engineer must be knowledgeable on the change of pressure as the system increases in complexity. The picture to the right of the screen is a snip from an ACT video that shows the performance of a pumped two-phase system as parallel evaporator plates are turned on and off. This video is accessible via ACT's webpage. A well-designed system will be able to work with multiple evaporators. However, the solution is not straightforward. The system must also accommodate both liquid and vapor flows. This means that understanding and knowing the vapor quality throughout the system is critical. And finally, there are very few programs that accurately model pressure drops in these two-phase systems. It is critical the designer has the ability to calculate and model this complex design. When we discussed the loop thermosiphon, we talked about the need for gravity to drive the fluid back to the evaporator. A pump two-phase system does not need that. However, to prove out the theory that the liquid would not fall to gravity control, ACT set up a lab test with two-phase heat sinks. One of the heat sinks has the fluid inlet at the top, while the other has the fluid inlet at the bottom. A close-up look at the evaporator number 2, the one with the fluid entering at the bottom, shows bubbles at the bottom of the heatsink. This indicates some gravity insensitivity. To continue looking at test results, our next slide proves out the high degree of isothermality capability of a pump two-phase system. In this design, both the top and bottom plates had several high heat flux diodes, which were required to maintain a temperature of 25 plus or minus 2 C. The system was first modeled by an in-house code developed by ACT. After completion of the model, ACT built and tested the two cold plates. The experimental test results proved out the isothermality capability by holding the diodes to nearly 25 plus or minus 1 C. The test results also validated the developed model and were further validated with a more accurate curve by the customer. This shows the capability of a pump two-phase system to not only handle the high heat flux, but also meet a high degree of isothermality in critical situations. In January of 2019, ACT expanded its pump two-phase portfolio by acquiring the Parker Precision Cooling line. The standard pump two-phase system was designed for high-efficiency, supercapacity, variable speed drives. It has been used in various platforms and has proven the ability for the unit to meet ruggedization standards since it has been fielded in harsh environments. The second unit was designed for high-performance, medium-voltage drives. This design includes a power electronics-specific evaporator cold plate that is highly reliable and has a microchannel heat exchanger under every IGBT placement zone. The cooling system uses a redundant pump design with variable speed. The pumps are placed on a pump tray. That pump tray is designed to easily remove for service or replacement. The design uses R134A as the coolant media with an air-cooled microchannel condenser located at the top of the unit. The plumbing leverages dry brake coupling connections that are used for the ease of assembly and shipment. In this webinar, we have addressed typical challenges many engineers experience as they design high-power power electronics systems. We've identified that two-phase technology allows for higher heat flux, higher total power, and promotes several system-level advantages, such as the use of dielectric fluids and package flexibility. The ACT enclosure coolers are a simple way to exchange heat from inside the electronics cabinet while still maintaining that dust and water-resistant feel. The loop thermosiphon provides that high heat transport capability, given the location of the heatsink is gravitationally above the power electronics. And finally, pump two-phase, which offers the high power operation, transfers the heat long distances, and supports flexibility in the design. If you have any questions regarding any of the technologies discussed in today's webinar, please contact ACT at info@one-act.com. Thank you for watching.
Thank you, Kimberly. Audience, do you have a question or two? Make sure to enter them into the Q&A panel now. Kimberly had to step out, so Andy Slippy, Product Development Engineer 2 from ACT, will be answering your questions.
Hello, this is Andy from ACT.
Hi, audience, please continue to get in your questions, and Andy, we will continue to answer some of these questions that we have here. Our first question is, how can we make these concepts and products to use in small size power electronics?
Yeah, so I'm not 100% sure what size, small size, they're talking about here, but this technology is pretty scalable to pretty much any size. I'm not sure if they want to put in a follow-up question with what more specific sizes they're talking about.
Okay, well, our next question is, what happens if you have more waste heat than expected in a pumped two-phase system?
Hi, this is Scott, also of ACT. It's like any thermal design. If you design it to run at a given maximum electronics temperature for a given power, if you exceed that power, the thermal resistances and all systems dumping to air, either air or water, will be fairly linear with power. So if you design it for a given power at a given operating temperature, if you have more power, the evaporator temperature will rise, but it can still carry those powers. With the pump two-phase systems, there is a decent amount of margin in there with the quality leaving the cold plates. So with some controls and some regulations, we can handle higher powers, and by controlling the pressure in the system, even keep it at a very similar constant power. But we typically like to design for worst case powers and know what that is, so to assure the system.
Okay. Our next question is, does pumped two-phase work like a refrigerator?
No, not exactly. So a refrigerator would use a compressor on the vapor side, and you're actually compressing the fluid. Takes a lot more power. You're putting work into the system. The pump, we're actually pumping the liquid in the pump two-phase system. The difference there in terms of heat transfer is that with the refrigerator you can actually generate temperature lift, so you can cool things cooler than your ultimate heat sink. With the pump two-phase, as was talked about, I don't know if it was talked about in that section, but one part in the presentation, you can only project heat assuming your ambient is colder than the temperature that you're trying to hold your devices.
Okay, our next question, how far does long distance refer to in pumped two-phase system?
Yeah, long distance is really going to be relative to your pump size. So the limit is how big of a pump do you want to put on it. We talk about it being long distance as opposed to the passive solutions, which are going to be limited more by physics and how far a liquid can go based on going against gravity and that sort of thing. With the pump two-phase, pretty much the pump is your limit.
All right. Our next question is, what are the challenges to model two pressure drops in two-phase systems?
Yeah, so there's a lot of challenge in modeling the pressure drop in a two-phase system. Standard CFD codes will not capture that very accurately at all. And there's a number of empirical correlations for two-phase pressure drops, but they're all very specific to very certain circumstances and tend to not agree with each other depending on the data set. So there's a lot of challenges there. We have the physics, the reason physically why there's a challenge there is you have this liquid changing to a vapor. The density is changing. very significantly, and what exactly is happening in terms of the physics there depends partly on how vigorously it's boiling, whether it's more passively evaporating rather than like bubbling and boiling. There's a lot of factors in that. So yeah, modeling that is a challenge. We have some ways that we approximate that have proved pretty accurate for the types of cold plates that we've developed, but there's not a single way of doing that yet.
Okay, and another question is, what is the recommended simulation software for designing with these products?
So we use in-house codes for actually designing the loops. If you're looking at implementing this and wanting a way of simulating it, there you can make something work in a number of FEA simulations. You would need to probably talk to us about your application, and we could give you some numbers that you could use to estimate things.
Okay, the next question, what kind of pumps do you use for P2P, and is there a high leak or failure rate on the pump?
The pumps that we use are typically positive displacement pumps, so that you're ensuring a steady flow rate. And then we have a number of pumps that we have a lot of life test data on it with very robust gear systems in there to withstand a long life. So we're not having a huge failure rate. In terms of leak rate, they have to be hermetically sealed pumps, especially with the refrigerant, or else that's not going to work right. So there's not a high leak rate as long as you're using a hermetically sealed pump.
Okay, the next question, does pump to two-phase system use more refrigerant than a compressor-based two-phase?
Yeah, I think there would be more total refrigerant in the system potentially. Again, it's going to depend on how far you're going and how long your lines are and that sort of thing. But since we're pumping liquid, there's more of the system is actually liquid as opposed to vapor. In a vapor compression system, a lot of your lines are going to be filled with vapor. So in terms of mass of refrigerant, there'll be more of it in there.
Okay, another question. What are the maximum heat flux levels in the evaporators of passive and pump systems?
Maximum heat flux levels in passive systems, I guess the same for both. Yeah, it's pretty much the same for both, because we're evaporating similarly in both, and we're typically up in the 25 to 50 watts per centimeter squared heat flux levels. We have looked at some higher heat fluxes than that in certain applications that can work. The heat fluxes aren't necessarily limits in terms of like everything's going to explode when you are higher than that heat flux. You're just going to start incurring larger temperature deltas. The thermal resistances are not going to be as low as hoped, as is typically hoped for when you start getting higher heat fluxes.
Okay. Our next question, what are the subcooling effects on two-phase thermosiphon loop performance?
Yeah, this is Scott. You do want to have some subcooling so you can get your gravity head in the thermosiphons, but it's really just the temperature gradient in the system is really set by the pressure drop of the vapor in the returning liquid. So the evaporator will just run hotter than the condenser just by the pressure drops for the vapor flow at the power you're doing. Coming out of the condenser, it is designed to be fully condensed fluid, so you'll have some minor subcooling there. But as the condenser rises or cools down, your evaporators typically float along with that at a given gradient.
Okay. The next question, are the pumps mechanically coupled?
To each other or to the motor? Typically, if we have multiple pumps in a system, they're independent. They are mechanically coupled to a motor drive.
Yeah, I think.
And the sealed systems.
Yeah,
magnetically driven.
Yeah, they can be magnetically driven pumps as well, so that the shafts from the motor to the pumps are not necessarily. So you're not dealing with the seals of a mechanical couple there.
So we do both.
But yeah, both can.
Okay, and the next question, what is the max size of the pump?
There is no real limiting factor. The higher the power, the longer the transport distance, the more flow rate and pressure head you need. So you can go up to very large pumps if required. Typically, the pumps are much smaller, require much less flow rate, as Kim pointed out in the presentation, than single phase. So typically less than a single phase cooling system, but we can always scale up to whatever flow rates and powers and heads required to the transport distance. I don't think there's any real upper limit to that size as long as the pumps are available.
All right, the next question, any comment for selecting pumps for a two-phase loop?
Yeah, I mean, we kind of talked about this already, that the pumps would be positive displacement pumps, and that they provide the right flow rate for your loop and can withstand the life expectancy.
They need to be hermetically sealed, long life pumps, and that can handle, as Andy said, the flow and the head required to circulate fluid.
Okay. The next question is there a minimum heat flux for P2P?
No, there's not really a minimum flux. The lower your heat flux is, or the lower your power is, we can have even smaller pumps and more lower flow rates. So, it should work for any low heat flux.
Okay, and the next question, can a passive two-phase fit into a typical desktop chassis?
It should certainly be able to, depending on the powers that you're looking at, but the amount of powers being generated in a typical desktop chassis should allow that. Passive. Yeah. Certainly. Yeah. Sorry.
Systems are used.
I was still thinking active two-phase, but yeah, passive, definitely.
Okay, the next question. What are the major design considerations for cold plates for a two-phase cooling system?
So for the cold plate, it's mostly about getting refrigerant or the coolant, whatever it might be, to where the actual heat loads are, and balancing that flow rate. It's a lot of manifolding, making sure that you have the right amount of flow at the right places based on your heat loads, and being able to account for changing heat loads there. There's some other design considerations in terms of gravity and ensuring that the channels are such that they will be gravity independent, as was talked about in the presentation. If you don't do your design quite right, it might not be gravity independent. Yeah. So and then considering also what was talked about in the presentation about knowing what the quality, the percentage of vapor is as you're going through your cold plate, and making sure that you're not getting to a point at any point in your cold plate where you're running out of liquid completely. So considering all these things and like I said, a lot of that has to do with, in terms of design, is distributing the flow to the right places, and keeping you from having more flow than you absolutely need as well.
Okay, well, I think we are just about out of time for now. So our thanks again to Kimberly and Andy, as well as Advanced Cooling Technologies. All questions submitted will be posted on our website with answers. So even if we didn't get to your question during the session, you'll still be able to find it there. Check your email, because in about 24 hours, you'll be receiving a message with a link to the on-demand version of this presentation. I'm Jennifer Arroyo with Electronics Cooling. Thanks again for participating in Thermal Live 2019.